Flight safety is a top priority in the aviation industry. Whether it's a commercial airliner, flying thousands of passengers across the globe, or a small private plane, ensuring that flights are safe is essential to maintaining public trust. The importance of flight safety cannot be overstated, as any lapse in safety can have catastrophic consequences. Despite the attention aircraft accidents receive in the media, air travel remains one of the safest modes of transportation. Statistically, plane crashes are rare events, with millions of flights occurring annually without incident. However, this does not mean that safety measures should be taken lightly. The aviation industry continually works to prevent accidents through rigorous safety protocols, cutting-edge technology, and detailed training for both pilots and ground crew. Aircraft are complex machines, and although the probability of failure is low, certain factors can still contribute to accidents or incidents. Understanding common aircraft failures, as well as the procedures in place to address them, is crucial for both aviation professionals and passengers alike. Common aircraft failures. Engine failures. Engines are the heart of an aircraft, providing the necessary thrust to keep it airborne. However, like all mechanical systems, they are not immune to failure. Engine malfunctions can occur for several reasons, including fuel contamination, mechanical wear, or even a bird strike. In rare cases, a total engine failure can occur mid-flight. When an engine fails, it doesn't necessarily mean a crash is imminent. Modern aircraft are equipped with multiple engines, which allow for continued flight even if one engine fails. Pilots are trained to handle engine failures through emergency procedures, such as flying to the nearest airport or performing an emergency landing. The aircraft's design also ensures that the remaining engines can compensate for the loss of power. For instance, the famous Miracle on the Hudson flight, U.S. Airways Flight 1549, in 2009, demonstrated how well-trained pilots and a well-designed aircraft can manage engine failure. After both engines failed due to a bird strike, Captain Chesley Sully Sullenberger and First Officer Jeffrey Skiles successfully performed an emergency water landing, saving all 155 people on board. Flight control system problems. The flight control system, which includes autopilot and manual flight controls, is crucial for keeping an aircraft stable during flight. Autopilot systems, in particular, help reduce pilot workload and increase efficiency, especially during long-haul flights. However, issues can arise when these systems malfunction or fail to respond as expected. Problems with autopilot systems may occur due to electrical faults, software errors, or incorrect inputs by the crew. A malfunctioning autopilot can lead to issues such as uncoordinated turns, loss of altitude, or incorrect flight paths. In these situations, pilots must take manual control of the aircraft and work quickly to restore stability. In extreme cases, as seen in the tragic crash of Air France Flight 447 in 2009, autopilot malfunction combined with a loss of communication between the cockpit and the flight crew can result in fatal consequences. The crash was partially attributed to the pilot's inability to correctly interpret the automatic system's data in the context of changing weather conditions. Weather factors. Weather is one of the most unpredictable variables in aviation. Strong winds, turbulence, thunderstorms, and icy conditions can all affect an aircraft's performance. Pilots receive extensive training to manage these adverse weather conditions, but the severity of a storm can still pose a risk, particularly if it occurs unexpectedly. For example, turbulence is a common weather-related phenomenon that can cause discomfort for passengers, but it rarely leads to accidents. However, severe turbulence, especially when encountered suddenly, can be dangerous, causing injuries to passengers and crew who are not secured. Pilots are trained to avoid areas of intense turbulence by consulting weather reports and rerouting their flights if necessary. Thunderstorms present additional challenges due to lightning strikes, hail, and severe turbulence. Aircraft are designed to withstand lightning, but pilots must avoid flying directly into thunderstorms to prevent other risks, such as hail damage or severe wind shear, which can drastically affect the aircraft's speed and altitude. Structural issues. Aircraft are built to endure the stresses of flight, but over time, even the most durable aircraft can develop structural problems. These can include cracks or corrosion in the fuselage, wings, or other key components. Such issues may arise due to wear and tear, manufacturing defects, or exposure to extreme weather conditions. Regular maintenance and inspections are essential to detecting these problems before they escalate into a safety risk. One of the most notable structural failures in aviation history was the 1989 crash of United Airlines Flight 232. The aircraft's tail-mounted engine failed, causing a hydraulic system failure that left the pilots without full control of the plane. Although the plane was severely damaged, the flight crew's quick thinking and the teamwork of both the pilots and the passengers enabled a successful crash landing. This incident led to improvements in aircraft structural integrity and emergency training procedures, pilot training, and preventative measures. To minimize the risk of accidents due to aircraft failures, pilots undergo extensive training. Flight schools teach both basic flying skills and advanced techniques for handling emergencies, such as engine failures, autopilot malfunctions, and severe weather conditions. Simulation training is a key component, allowing pilots to practice responding to a wide range of scenarios in a safe environment. In addition to emergency protocols, pilots are trained to understand the systems and mechanisms of the aircraft in depth. Regular refresher courses ensure that pilots stay up to date on the latest safety practices and technological advancements in aviation. Modern aviation technology also plays a significant role in preventing accidents. For instance, many aircraft are now equipped with advanced warning systems such as terrain awareness and warning systems, TOWs, which alert pilots to potential terrain collisions, and traffic collision avoidance systems, TCAS, which help prevent mid-air collisions. These systems work in tandem with the skills of the pilots to maintain a high level of safety. Moreover, advancements in maintenance technology, such as automated diagnostic tools, have made it easier to identify potential problems before they become critical. These tools allow for real-time monitoring of aircraft systems, ensuring that any issues are addressed promptly and before they can affect flight operations. While aircraft failures are rare, they remain a critical consideration for the aviation industry. By understanding the common causes of failure, such as engine malfunctions, flight control system problems, weather factors, and structural issues, both pilots and passengers can appreciate the complex nature of air travel safety. With continuous advancements in technology and training, the aviation industry strives to make flying safer than ever before. This is a reminder that, even in the rarest of circumstances, flight safety remains a priority that affects every aspect of modern aviation. While aviation has made tremendous strides in safety over the past century, it is not without its dark moments. Some of the most significant advancements in flight safety have been driven by tragic accidents. Each of these events serves as a reminder that the aviation industry must constantly evolve, learning from past mistakes to ensure a safer future for passengers and crews alike. This chapter will revisit some of the most infamous aircraft accidents in history. The crash of a DC-10 at Sioux City, the American Airlines Flight 191 disaster, and the mysterious disappearance of Malaysia Airlines Flight MH370. By analyzing these incidents, we can better understand how flight safety has advanced and what lessons have been learned to help prevent future tragedies. Famous case studies. The Sioux City DC-10 crash, 1989. On July 19, 1989, United Airlines Flight 232, a DC-10 aircraft, was en route from Denver to Chicago when it suffered a catastrophic engine failure. The failure caused the loss of the plane's hydraulic system, which meant that the pilots lost the ability to control critical functions such as the rudder and ailerons. The crew was left with limited control over the aircraft, and the plane was no longer able to maintain a steady course. Despite the serious mechanical failures, the flight crew, led by Captain Al Haynes, did everything they could to control the plane and guide it to an emergency landing. Using only throttle control and the remaining rudder, they managed to keep the plane relatively stable and aimed for Sioux City Airport, where they attempted an emergency landing. Tragically, while many lives were lost, the crew's quick thinking and ability to work with limited resources saved the lives of over 180 people. The crash landed in a fiery explosion, and 112 of the 296 passengers aboard died. However, the heroic efforts of the crew and the cooperation of the passengers were praised for minimizing the loss of life. The incident led to significant changes in aircraft design and crew training. The DC-10 was modified to prevent similar hydraulic failures in the future, and flight crews began receiving more advanced training on how to handle complex emergencies with limited resources. The tragedy also prompted improvements in cockpit communication and crew coordination. American Airlines Flight 191, 1979. On May 25, 1979, American Airlines Flight 191, a McDonnell Douglas DC-10, crashed shortly after takeoff from Chicago O'Hare International Airport. The plane was carrying 271 people when the left engine detached from the wing shortly after takeoff. This engine failure resulted in a loss of hydraulic power, and the plane quickly became uncontrollable. The accident occurred when a maintenance error led to the engine's pylon, the structure holding the engine to the wing, being improperly installed. During takeoff, the engine was not secured properly, and it detached, damaging critical control systems. As a result, the plane pitched uncontrollably and crashed just over a mile from the runway, killing all 271 people on board. The crash of Flight 191 was one of the deadliest in U.S. history and raised serious questions about aircraft maintenance and safety. It highlighted the need for better quality control in aircraft manufacturing and maintenance practices, as well as the importance of thoroughly training maintenance personnel. The aftermath of the tragedy led to a significant overhaul of maintenance procedures in the aviation industry. A special emphasis was placed on regular inspections and stricter guidelines for attaching engines and other vital components. Additionally, this accident contributed to the development of more stringent regulations on the certification of aircraft parts and the implementation of better safety checks. The disappearance of Malaysia Airlines, Flight MH370, 2014. On March 8, 2014, Malaysia Airlines Flight MH370, a Boeing 777, disappeared from radar screens while flying from Kuala Lumpur to Beijing. The plane was carrying 239 passengers and crew members, and despite an extensive search operation, the aircraft was never found in its entirety. What followed was one of the most baffling and mysterious aviation disasters in history. Early in the flight, MH370 made a routine transmission, but soon after, the aircraft's communication systems were deliberately disabled. The plane's last known location was near the southern Indian Ocean, but the precise reason for its disappearance remains unknown. Investigations suggested that the aircraft's flight path was altered manually, leading to numerous theories, including mechanical failure, hijacking, or even intentional actions by the flight crew. The search for MH370 became the longest and most expensive in aviation history, spanning several years and covering vast areas of ocean. Though some wreckage from the plane was found on distant shores, the main wreckage has never been located. The disappearance of Flight MH370 raised serious questions about aircraft communication and tracking systems. The lack of real-time data led to delays in understanding the aircraft's whereabouts, which hampered the search efforts. In response, the aviation industry has since worked to improve flight tracking systems, including satellite-based monitoring systems that provide more accurate and immediate information about an aircraft's location. New recommendations also include the ability for aircraft to send automatic position reports at more frequent intervals, particularly in cases of abnormal flight behavior. The disappearance also triggered an international debate on the psychological screening of flight crews, with some suggesting that the pilots might have been involved in the incident. As a result, the aviation industry has made greater efforts to improve mental health evaluations and support systems for airline staff. The safety improvements from these tragedies. Each of the incidents mentioned above has played a pivotal role in shaping modern aviation safety standards. From the Sioux City crash to the disappearance of Flight MH370, every major accident has provided the aviation industry with critical insights into the potential weaknesses in flight operations, technology, and procedures. Aircraft design and engineering. After the Sioux City crash, there were significant upgrades to the DC-10's hydraulic system, as well as changes in the design of its tail-mounted engine to prevent similar failures. Additionally, the training of flight crews was enhanced to ensure that pilots could effectively handle complicated emergency scenarios. The emphasis shifted toward more practical emergency drills and hands-on experience for flight crews in simulators. Maintenance procedures. The American Airlines Flight 191 disaster led to a dramatic improvement in aircraft maintenance standards. Airlines adopted more rigorous inspection schedules and safety checks, especially when it came to securing critical components like engines. The incident also underscored the importance of thoroughly training maintenance staff and improving communication between ground crews and flight crews. Flight tracking and communication. The disappearance of MH370 was a wake-up call for the aviation industry, emphasizing the need for real-time tracking of aircraft, particularly when communication with the aircraft is lost. The international aviation community has worked on improving tracking technology, ensuring that planes can be monitored from takeoff to landing, even over remote areas. The idea of using satellite technology for continuous tracking is one of the key solutions that have been adopted since this tragedy. Crew training and psychological screening. Both the DC-10 crash and the MH370 incident led to increased attention on the psychological well-being of flight crews. Screening processes for pilots have been revised, with a stronger focus on mental health support and ensuring that pilots are not suffering from conditions that could impair their ability to perform under pressure. The accidents, whether caused by mechanical failure, human error, or unknown factors, have left an indelible mark on aviation safety. Though the loss of life in each of these incidents is a tragedy, they have driven the aviation industry to make improvements that have ultimately saved countless lives in the years since. Each disaster has become a stepping stone for change, teaching lessons that have led to better aircraft design, stronger regulations, and more effective training. By learning from past tragedies, the aviation industry has made remarkable progress in creating safer skies for everyone. The aviation industry has come a long way since the early days of flight, achieving an unparalleled level of safety. However, as technology continues to advance, new challenges arise that require careful consideration and adaptation. From the rise of unmanned aerial vehicles, UAVs, to increasing automation in flight decks, the future of aviation safety will look quite different from the past. In this chapter, we will explore how modern aviation is addressing emerging challenges, including the use of drones and autonomous flight technologies, and the increasing reliance on data and simulation for improving safety. We will also look at the potential threats posed by global trends like climate change and increasing air traffic, and how the industry is preparing for these future risks. Technological advancements in modern aviation safety. Flight data monitoring and analysis. One of the most significant innovations in aviation safety has been the development of advanced flight data monitoring and analysis systems. These systems continuously collect and analyze data from an aircraft's various sensors, including engine performance, speed, altitude, and even weather conditions. This data is transmitted in real time to ground control stations, where it is monitored for any irregularities. The ability to monitor flight data in real time provides a powerful tool for predicting potential failures before they happen. For instance, by analyzing trends in engine temperature, fuel consumption, and other key parameters, aviation engineers can detect patterns that might indicate an impending failure. This allows airlines to perform targeted maintenance or repairs before a problem becomes critical, ultimately preventing accidents and minimizing downtime. Moreover, post-flight data analysis allows aviation experts to review the performance of an aircraft after each flight. This helps identify any mechanical issues or operational inefficiencies that could affect safety. As airlines adopt predictive maintenance models based on data analysis, the likelihood of unexpected mechanical failures is greatly reduced. The integration of artificial intelligence, AI, and machine learning into flight data systems is another step forward. AI can process vast amounts of flight data, identify potential risks, and even suggest preventative actions for aircraft operators. This technology has the potential to revolutionize aviation safety by improving the accuracy of risk assessments and enhancing decision-making processes. Enhanced pilot and crew training with virtual reality, VR. While technology plays a huge role in improving aircraft systems, human error remains a significant factor in many aviation accidents. As a result, pilot and crew training is one of the most critical components of modern flight safety. Over the years, aviation training has evolved significantly, with virtual reality, VR technology, offering a major breakthrough. VR allows pilots to immerse themselves in realistic flight simulations, where they can experience a variety of emergency situations without leaving the ground. These simulations can replicate complex scenarios, such as engine failures, system malfunctions, or severe weather conditions, providing pilots with the opportunity to practice their responses in a controlled, risk-free environment. In addition to traditional flight simulators, VR offers a more interactive and cost-effective training method. It provides a safe and engaging platform for pilots to practice decision-making, learn emergency protocols, and improve their overall situational awareness. VR training also helps pilots develop better muscle memory and decision-making skills, both of which are crucial in high-pressure situations. Beyond pilots, crew members, including cabin crew and air traffic controllers, are also benefiting from VR training. Cabin crew can practice evacuations, handling difficult passengers, and responding to medical emergencies. Air traffic controllers can simulate high-volume air traffic scenarios to improve their coordination and decision-making in real time. These technologies ensure that every member of the flight crew is better prepared for any situation that may arise. Challenges with autopilot and unmanned aerial vehicles, UAVs. One of the most transformative trends in aviation is the increasing use of autopilot systems and the potential for fully autonomous aircraft. While autopilot technology has been in use for decades, advances in AI and machine learning are pushing the boundaries of what is possible. Some modern aircraft can now fly with minimal input from pilots, allowing them to focus on monitoring systems and handling emergencies. However, as autopilot systems become more advanced, they also present new safety challenges. One concern is the potential for autopilot failures or system errors that may go unnoticed by the flight crew. In certain cases, pilots may become overly reliant on autopilot systems, leading to a decrease in manual flying skills. This could be a problem in situations where the autopilot is disengaged, and the pilots need to take immediate control of the aircraft. The prospect of fully autonomous aircraft, which do not require a human pilot, raises further concerns. While autonomous flight could reduce human error and increase operational efficiency, the technology is still in its infancy, and many experts believe that a fully autonomous commercial flight is many years, if not decades, away. Until then, there are ongoing discussions about the safety implications of removing pilots from the cockpit entirely, particularly in terms of how such systems would handle emergency situations or unexpected system failures. Meanwhile, the rise of unmanned aerial vehicles, UAVs, commonly known as drones, is another challenge for aviation safety. Drones are becoming increasingly popular for commercial and recreational use, but their presence in controlled airspace raises concerns about collisions with manned aircraft, especially near airports. To address this issue, aviation authorities are developing new regulations for drone operators, including the need for drones to have geo-fencing technology and automated collision avoidance systems. Future challenges and the direction of aviation safety. The impact of globalization and climate change on aviation safety. As air travel becomes more accessible and affordable, The aviation industry is experiencing rapid growth in terms of passenger numbers and flight frequency. According to the International Air Transport Association, IATA, global air traffic is expected to continue growing over the coming decades. While this is great for the aviation economy, it also brings significant challenges related to airspace congestion and increasing pressure on air traffic control systems. As air traffic increases, the risk of mid-air collisions or congestion-related delays becomes more likely. To mitigate these risks, aviation authorities are investing in advanced air traffic management technologies, such as satellite-based navigation systems and automatic dependent surveillance broadcast, ADSB. These systems enable more precise tracking of aircraft and help to better manage the flow of traffic in busy airspaces. At the same time, climate change is having an undeniable impact on aviation. Extreme weather events, such as hurricanes, heat waves, and heavy rain, are becoming more frequent and intense. These weather changes not only disrupt flight schedules, but also pose serious risks to flight safety. For example, extreme temperatures can affect the performance of aircraft engines and reduce the amount of lift generated by the wings. The aviation industry is responding to these challenges by adopting more sustainable practices, such as the development of greener aircraft and the use of biofuels to reduce carbon emissions. Additionally, airlines and airports are investing in infrastructure that can better withstand the effects of climate change, ensuring that airports remain operational even in the face of extreme weather. Balancing technological advancements with passenger safety. As aviation technology continues to evolve, a central challenge for the industry is ensuring that advancements do not compromise passenger safety. While new technologies such as AI, autonomous flight, and advanced data monitoring systems hold great promise for improving safety and efficiency, they also introduce new risks. The aviation industry must find ways to strike a balance between embracing innovation and maintaining the highest safety standards. One of the key ways this balance is achieved is through rigorous testing and certification processes. Every new technology undergoes extensive evaluation to ensure that it meets safety standards before being deployed in commercial flights. Additionally, airlines and regulatory bodies collaborate to ensure that pilots, crew, and maintenance personnel receive the proper training to handle new technologies safely. Furthermore, the introduction of new technology often requires updates to existing regulations. For example, the rise of drones has led to the creation of new airspace management policies, while the increasing use of automation in flight decks is prompting discussions about pilot training and certification requirements. The challenge is to ensure that regulations evolve alongside technology without stifling innovation or compromising safety. The future of aviation safety is both exciting and complex. As the industry embraces new technologies such as AI, autonomous flight, and UAVs, the potential for improved safety and efficiency is vast. However, these advancements also bring new challenges that must be carefully managed. By investing in new technologies, improving training methods, and addressing global challenges such as air traffic congestion and climate change, the aviation industry is positioning itself to continue making flying safer for everyone. As we look to the future, it is clear that the key to successful aviation safety lies in the continued integration of technology, human expertise, and effective regulation.